Oh, I posted a problem set. Did you see that? So problem set 1. It's due in lab the week of, I think it was March 31st to April 3rd, maybe that would be April 3rd or 4th. So all of you, I guess, will be doing it on Friday the 3rd or Friday the 4th, whatever day that is. And so remember, the way we're going to do problem sets is, so, you know, do it the way you normally would. And then, but instead of turning the paper in, you're going to bring the paper to lab and just sort of explain to me how you did it so I can ask questions and just make sure you understand what you're doing. And so I can make corrections, you know, real-time corrections instead of you waiting to get the paper back, and then maybe you do and maybe you don't look at any comments I make. Maybe I do and maybe I don't write any comments. You know what I mean? I think it's just a better way to make corrections. So the grade will be based on your sort of explanation of what you did in the work. That's right. Yeah, and if I'll be here, like if you want to come and work on problems or whatever, feel free. I'll be in the lab, but right, we don't have a new lab, so you don't have to be here. And so just remember, once you finish the assignment, so say you finish the assignment the Tuesday before lab or whatever, since it's going to be 3 days until lab, it would probably be a good idea before you come to lab to just quickly remind yourself the steps of how you did the problem, okay? It just makes it go more smoothly. It makes it more clear to me that you know what you're talking about. Okay, any questions about that? All right, so before break, we started talking about electricity. And so I talked about what a charge was. And I want to just sort of, before I get back into definitions of things and calculations, I want to just talk about where I'm going with all this stuff. So electric power comes from charged particles moving through force fields. Well, and actually, let's even make it simpler than that. Skip the force fields part. Just charged particles in motion, okay? If you have charged particles that are moving, that's called electric current, and that's where all electric power comes from. Everything that has to do with electricity comes from the motion of charged particles. Oh, we want to hear something else? This is what my son told my wife yesterday about this is, I believe, his own, so he's like 6, but he came up with his own theory for the 4 stages of grief. And the first one was you're so sad you feel like you're going to throw up all the time. And the second one, I don't know, the second one was just like being sad all the time, like you don't like to look at things that remind you of the person or whatever. And then the third one was it's still sad when you think about it, but you're happy enough now to like enjoy like music and pictures and stuff that remind you of the person. And the fourth one is you're super happy, you're glad they're dead. And then he's like, that fourth one is only for your enemies, though.
At 6 years old?
Yeah.
Oh, man. That's got to tear you up no matter what.
Yeah. Okay, so all electric power comes from charged particles in motion. And so how do charged particles, how are they put into motion? This motion of charged particles comes from, and the motion of these charged particles, and the ones that we're talking about being in motion, you can think of as a collection of test charges. Remember, the test charges I mentioned last time are the ones that you're talking about, that those are like your chosen objects. So like if you did a free body diagram, you'd do a free body diagram of the test charge. And the motion of these test charges comes from the force fields of other charged particles. And these other charged particles are the fixed charges. Okay? So the ones that are the fixed charges produce these force fields. These force fields of the fixed charges make the test charges move, and that motion of the test charges is electric current. And that's an electric current is what we care about. That's what turns lights on and all that stuff. Okay, so there are two ways to talk about the forces produced by the fixed charges. The first is force fields, which is what we've started to talk about. And this will lead us to the idea of electric fields. And the second one is these force fields are conservative forces. Anyone remember when did we talk about conservative forces in first semester physics? Anyone remember? Does that word ring a bell? So there were two types of conservative forces that the people who took it from me that we talked about. The forces produced by gravity and the forces produced by springs. Those were the only two we could talk about. The idea of a conservative force is one where as long as you know the object's location, you know the force. So if you think about it that way, a conservative force is that's the same definition as a force field. So anything that you can represent by a force field is a conservative force, okay? And conservative forces there's a way to represent the work done by conservative forces that you can't do for non-conservative forces. Anyone remember what that is? So when we started talking about work, what was special about gravity and springs? What did we have for those that we didn't have for other forces? Monkeys? No. Potential energy.
Potential.
Yeah. So, so anything that has a force field, anything that you can represent as a force field, you can represent, you can also talk about as potential energy. And so the other way that we can talk about the forces of these fixed charges is potential energy. And in the same way that force fields is going to lead us to this sort of obscure idea of electric fields, potential energy is going to lead us to the idea of voltage. And that's kind of cool because that's, voltage is what you're used to talking about, like, you know, more practically speaking, that voltage is what makes current go. You know, like you talk about the voltage in an electric socket, and if you plug copper wires into an electric socket, that voltage makes current flow through the wire to the light or the device or whatever. Okay. So this is kind of a roadmap of where we're going with this discussion. In practice, so this doesn't have to be the case. I mean, you could make electric current by having the motion of 1/2 Coulomb charges, big balls of charge, you know, and if they're moving, that would be electric current. But in practice, it's always the same type of test charge that moves to cause electricity. So in practice, the test charge is always an electron. It's always the motion of electrons that causes electric current. And not one electron, you know, millions of electrons, maybe billions of electrons. It's always an electron. Okay. I gave Coulombs Law last time. And Coulombs Law, I gave it as the force between two particles is equal to 8.988 times 10 to the 9th times the absolute value of one charge times the absolute value of the second charge divided by the square of the distance between them. And I gave directions also. The force is attractive, so the two particles are pulled together if Q1 and Q2 have the same sign. No, have opposite signs, sorry. And the force is repulsive if Q1 and Q2 have the same sign. Okay, so now I'm going to restate this in terms of, because I want to get in the habit of thinking in terms of test charges and fixed charges. So restated in terms of a test charge Q and a fixed charge capital Q. Then the force applied to the test charge by the fixed charge is F equal to 8.988 times 10 to the 9th times the absolute value of capital Q times the absolute value of lowercase q divided by r squared. And this force is toward the fixed charge if Q and capital Q have, so which one would this be? If we're talking about the force on the test charge, if the force on the test charge is toward the fixed charge, is that attractive or repulsive? Attractive, so would these have to have opposite signs or the same sign? Opposite, yep. And away from the fixed charge if Q and capital Q have the same signs. Okay, so any collection of fixed charges produces a force field for a specific test charge. But notice that the force field is different depending on the test charge. So if you use a different test charge, that force field changes. So the force field is different for each different test charge. So let's think about a couple cases. So let's say that we had, so first let's say that well, let's say that in both cases, so we're not going to change the fixed charge, we're just going to change the test charges. So let's say that our fixed charge is positive 1 Coulomb. And first, let's think about what its force field looks like if the test charge, lowercase q, is equal to negative 1.602 times 10 to the minus 19 coulombs. So what does this represent? What made me come up with that? Seems like a pretty arbitrary number. That's the charge of 1 electron, yeah. So say that we have a fixed charge of plus 1 coulombs and our test charge is an electron. What does that force field look like? Well, here's the fixed charge. And think about what Coulombs Law says. I'm not going to worry about actual magnitudes. I'm just going to worry about like the comparative magnitudes from point to point. So is this fixed charge going to attract the electron or repel it? It's going to attract it. Is it going to And so that means that the force vector on the test charge, on the electron, is always going to be pointed towards the fixed charge, right? And is it going to get bigger or smaller, that the magnitude of the force vector, as you get farther away from the fixed charge? Smaller. So this force field is going to look something like this. You know, I'm just taking a few representative points to try to give a sense of what this looks like. Of course, you know, the actual force field has one of these at every point. But the farther away you get, the smaller that vector gets. Okay? Does that make sense to everyone? Why is it getting smaller? Okay, so that goes back to this equation. And the key is that the fixed charge isn't, no matter where you are, the fixed charge stays the same. The test charge stays the same. The only thing that changes is r, the distance between the two charges. Okay? And so as r gets bigger, this f gets smaller. Okay? Which is good news, because imagine if the force applied between charges got bigger as things got farther away. The things you could see would have no effect on you. The things in outer space would be jerking you around, like, you know, that wouldn't work. So it has to be this way. Okay. Okay, so now let's think about the same fixed charge, but now we have a test charge. Okay, and this was an electron. Now we have a test charge of positive 1.602 times 10 to the minus 19 coulombs. What's this? That's a proton. It's also an anti-electron, but we're not going into that stuff in this class. Well, all of these particles have, there's antiparticles with opposite charge, and I believe a neutron is actually made up of, no, a proton is actually made up of a neutron and an anti-electron. That's why a proton and a neutron have basically the same mass. But for us, this is the mass of the charge of a proton. Okay, so what does this electric field look like? So there's our fixed charge of plus 1 coulomb. Is this force attractive or repulsive? And does the magnitude get bigger or smaller as you get farther away? Smaller still. And so this time the electric field, it looks the same, except the arrows are all going the other direction. Okay. And that's a little bit of a nuisance. So the fact that the force field depends on the test charge is a little bit of a nuisance. Because you have to know what the test charge is before you can talk about the force field, you know, before you can talk about the profile of fixed charges. So you need to know what your test charge is before you can describe your fixed charges. And so I said that that voltage is related to energy, right? And it's related to potential energy, and that potential energy is because you have a force field. Okay, so if you think of like an outlet or a battery or something, a battery is better, I guess. You describe it in terms of voltage. Imagine describing it in terms of force fields, okay? You wouldn't be able to say, you wouldn't be able to ask for a 9-volt battery, essentially. You'd say, I want a battery that's, that provides this many newtons of force. And the guy at Radio Shack would have to ask you what test charge you're planning to use. And you'd say, like, I don't know, I'm planning to use a bunch of stuff, you know? And so it just doesn't work very well. You want to be able to say a 9-volt battery, and even though voltage is related to potential energy, the same thing applies here. We want to, that battery is a set of fixed charges, and you want to be able to describe them without specifying what your test charges are going to be, okay? So that's the motivation for defining an electric field. For the definition of the electric field. The electric field is, so let's say it's made up of electric field vectors, capital E, where capital E is equal to the force vector divided by the test charge at each location. So it's still a field that's still made up of infinitely many vectors, but we've divided out the influence of the test charge. So now if we think about the example before, in A, for the test charge, lowercase q of, you know, an electron charge, the electric field looks like this. So here's your +1 Coulomb. Okay, so now we're talking about a negative test charge. What do the forces look like? Are they pointing towards it or away from it? They're all pointing towards it. They're getting smaller as you go away. But now we're dividing it by this, right? And so if you divide, so if each vector is going this way when it's a force vector and you divide it by a negative number, what does that do to the direction? Yep, makes it opposite. And so you end up with something that looks like this. And for part B, the test charge, lowercase q, is equal to plus 1.602 times 10 to the minus 19th coulombs. There's our plus 1 coulomb fixed charge. The forces are all going away. We're dividing by a positive number, so we end up with this again. Okay, and so in other words, you can describe the electric field of a set of fixed charges without specifying a test charge. Okay, so like for a wall outlet or a battery, we talk about it, like I said, in terms of voltage, but if we instead had gotten in the habit of talking about it in terms of force fields, we could describe a battery's electric field without, you know, and a battery could be sold in terms of its electric field without knowing what test charges it was going to be used with. Okay, so that's the benefit of it. One thing I want you to notice is numerically the electric field is the same as the force field for a plus 1 coulomb test charge. You just have to be careful with the units. With a force field, what are the units of the vectors in SI units? They're forces, so it's newtons. With the electric field vectors, the SI units are newtons per coulomb because you're dividing by coulombs. Okay, but you get the same number as if you calculated the forces for a plus 1 coulomb test charge. Besides the a point fixed charge, so that's the one that I just drew on the last page. There are two other profiles of fixed charges that you should get used to. Just, you know, you should kind of remember what these shapes look like. There are two other fixed charge collections whose electric fields should be familiar to you. Not they should be now, they should become familiar to you. You know what I mean? The first one is 2-point fixed charges of opposite signs. So here you have a positive, well, let me write it as positive capital Q. Here you have negative capital Q. Okay. The electric fields, so remember these are electric fields. All of these, so they follow, the paths of these vectors follow these sort of funny curved paths. But notice that they all just generally leave the positive and go to the negative, okay? And they make a pattern, they make patterns that look like this. Okay.
So in theory, the ones on the outside should be also smaller forces, correct?
That's right.
Okay.
Yep. And can anyone think of how you would, like if you had a year, you had all the time in the world, you know, that you wanted, but you had to somehow come up on your own with this electric field, how would you do it? What?
How would you make it?
Yeah, how would you figure out that this was the pattern? Say you didn't know this. You can actually calculate what this pattern is by calculating, so at each point on here, say you do it 1,000 times or something, calculate the force vector applied by this fixed charge. Then at that same location, calculate the force vector applied by this fixed charge. Add those two together, and then divide by Q to give an electric field vector. And you could actually calculate numerically what all of these are.
When you said, figure out the force vector of each charge, at which location? Is it like, would you have two separate locations or is that the same location?
Say it again. If
You're saying like, find the vector of each charge first?
Yeah.
And then you said by the
So what you would do is you would say like, you'd pick, this is as good a spot as any to start, you know? And so you'd figure out how far that is from this one, calculate that force, figure out how far it is from this one, calculate that force, add the two together, and then divide by small q, yeah. And the second type, the second profile of fixed charges that you should get used to is two parallel plates. These, like, theoretically, these are infinitely long, but this gives good results even when, as long as they're much longer than they are apart, you know? The distance up and down is longer than the distance between them. So if you have, say you have a positive plate here and a negative plate here, then in between these two plates, this is the cool thing about it, all of these electric field vectors are the exact same length, no matter where you are between these two plates. And the direction always goes straight from the positive plate to the negative plate. So between the plates, every electric field vector is identical. Mathematically, this will be nice because it'll let us calculate the work applied to a particle as it moves around in here. Because remember, work is the force times the displacement, and that force has to be constant throughout the whole motion. So you couldn't calculate the work as a particle moves around in here. Those forces keep changing. Does that make sense? But here we can. And practically speaking, this is useful because it approximates what happens in a capacitor, which is a useful electronic component. And a capacitor is a common and useful electronic component. Anyone know what a capacitor does? Anyone know what a flux capacitor does? Yeah, a flux capacitor takes you back in time. A normal capacitor stores up charge. So you can think of it as like, it's like a battery in a way. You store up all the positive charge over here, all the negative charge over here, and then when you connect those through a device or something, all the electrons flow from the negative side to the positive side, and they power the device as they go. We'll talk about flux capacitors in physics 3, if you take physics 3.
So the positive charges always attack negative charges?
They always, what?
The positive charges always attack negative charges?
Attract them?
Yeah.
Yeah. That's right.
And then the negative charges attract?
Yeah, so they, that attraction is always, so if there's two particles, they're always attracting each other. But I think the best way to think about it is only think of the force applied to whatever you're calling the test charge, you know? So if this one you're calling the fixed charge and this one you're calling the test charge, yes, this is attracting this one, but all we're thinking about is what's the force vector applied to the test charge over here. Okay, I think that's a better way to think about it. In order to simplify the drawing of electric fields, they're often represented by field lines. Rather than those electric field vectors, rather than those E vectors. And the definition of field lines, they're not really lines, they're curves. And they're curves that have the electric field vector tangent to them at each point. And in the two examples that I just gave, those are the red lines. So the benefit is that they're easy to draw. You do lose a bit of information. You don't get any magnitude information. If you're looking at the field lines, you only get direction information. So the downside is field lines give direction information, but no magnitude information. Okay, so let's think about those three fixed charge profiles that we're going to be talking about. So let's say one is a point charge. I guess let's make it positive. The field lines look like this. Just lines going out to infinity in every direction. And so what this tells you is, say that you wanted to know what direction the electric field vector was going at this point. It's tangent to this curve, so it has to be in this direction. You just don't know how big it is. And the second one is the positive and negative fixed charges. The field lines here look like this. And so say you wanted to know what the direction was of the electric field vector here. Well, it's tangent to this curve, so it has to be like that. Okay, so these field lines give you all the directional information, but again, they don't give you any magnitude information of those E vectors. You don't know how strong it is at that point, you just know the direction. And then the last one is for the fixed plates.
I'm sorry, can I get my water?
Yeah.
It's expensive. Sorry.
Okay, and then the last one is the fixed plates. And these are just lines going straight from the positive plate to the negative plate.
Are we using C in theory because it wouldn't arc at all, or is it just the way it is?
That's just the way it is. I mean, it's just a fact, a mathematical fact of how the math works, you know. So we're using it for two reasons. One is as a calculation exercise, and then the second one is that it turns out that a capacitor, which basically looks just like this, is a useful thing. So there's kind of a mathematical reason and a practical reason. Any questions about any of this yet? Okay, so now that's it for electric. That's it for force fields and electric fields. So now think back to physics 1. I just want to sort of explain like why we're going through these steps the way we are. remember that so in kinetics, we started with forces and Newton's laws. And then went on to work and energy. Okay? Those aren't really different topics. They're just two different ways of describing the same thing. And there are some topics that are easier to do, some calculations that are easier to do talking about forces, and some that are easier to do with energy. But if you knew enough about how to calculate stuff with both of these, any problem you could do with one, you could do with the other. Okay? So it's not new information. So that's the same thing we're going to do now. So we're done with force fields, and we're moving on to work and energy. And again, it's not, there's nothing that we can calculate with this that can't be calculated with this, and vice versa. But some things are easier this way and some things are easier this way. And remember that the key result that we're going to get to at the end of all this is we're heading towards voltage. We're heading towards voltage. Don't touch it. So, does anyone remember the relationship between work and potential energy? I brought this up sort of in passing last semester. So there is one. In fact, potential energy is just a way of calculating work. You could do everything in terms of calculating work. But when you have conservative forces, potential energy is a nice way to think about it. The calculations get easier. So let's think about so think of a 1 kilogram object falling 3 meters in a gravitational force field. So first, let's calculate the work. What's the work done by gravity? Well, what's the force that gravity is going to apply to that 1 kilogram object? Yep, exactly. So we have a force, if you think of like the free body diagram, we have a force down of 9.81 newtons. The displacement is 3 meters. These are in the same direction, so we're just going to multiply these two. And so the work is equal to 29.43. And what are the units?
And C,
This is, so we're talking about work.
force, no.
You could think about it this way, or also just remember that work is a change in energy due to application of a force, so it has to be joules. Yep. Okay. And now let's think about the change in potential energy. Does anyone, does anyone remember the definition of gravitational potential energy? So the gravitational potential energy is m times g times h. And so you can think of at the starting point, the initial is, so let's say we'll call the height at the starting point 3 meters and the height at the ending point 0 meters. So we have 1 kilogram times 9.81 times 3. So 29.43 joules. The final is 1 times 9.81 times 0, so 0. And so the change in potential energy is equal to the final minus the initial, so negative 29.43. Okay? So the work is always equal to negative change in potential energy. Okay, what am I doing with that? Okay, so we'll want to calculate the potential energy for calculating voltage. So notice that the equation above says we can find the potential energy two ways. Well, really find the change in potential energy two ways. The first one is calculate it directly. When we have a formula for potential energy. But that's not always going to be the case. So we won't always be able to do it that way. Or we can calculate the work and use the above relationship. That only works for us when the force is constant. Okay. Any questions about that? Yeah.
So for for the equation that we did, for the first one, the revised diagram ones,
Mhm.
that it was like 29 point, same thing, it's the same thing.
Yeah.
So that's just basically it for
The work?
yeah.
Was it for calculating the work or the potential energy?
Work and then you calculate the potential.
Yeah, so if you remember, work is equal to, the force vector dotted with the displacement vector, which is equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement. In this case, the displacement, well, the force vector was 0x, so this one's going to go away. And then negative 9.81. So we have a negative 9.81. Yeah, so I'll write it out here. So we have 0. If you did this in terms of vectors, you'd have 0 times 0 plus negative 9.81 times negative 3, and that gives you positive 29.43. So that's how you do it in terms of vectors. Okay, well, yep. Let's stop there, and I'll do some examples next time with both of those two ways of calculating change in potential energy. And we'll turn that into, figuring out voltage. If you have, what day is it? Thursday? I would say, so yeah, you have 5 days before class. I think it would be a good idea to go back through this because there's a lot of details, like you can do this one way or a second way, and then that you can do, I think you'll find the next class makes more sense if you spend a little time familiarizing yourself with all of this. Okay.